All right. So, welcome back and good afternoon to all of you. So, we shall start today's class in a few minutes. So, and today we are going to actually solve a few examples on Fourier transform. Okay. And this is uh, the fourth class on Fourier transform, Fourier analysis. We shall have one other class where we shall actually discuss different properties of Fourier transform, and then after that we shall discuss how we actually use this and in our analysis of systems and signals, right? So we shall study those later on. So yes, so today we shall actually be solving quite a few problems on Fourier transform. Again, I have just listed out the signals for which we are going to calculate the Fourier transform. So we shall start that shortly. And on the next class we shall be talking about the properties of Fourier transform, and there we shall talk about many properties of Fourier transform. But today one of the most important properties shall be taught, and which is the principle of duality of Fourier transform. Now you will soon realize that this is one of those properties which must be told before we can actually proceed into solving Fourier transform, calculating Fourier transform for different signals, because Fourier transform is inherently associated with complex analysis. Because you might already understood that while calculating Fourier transform we did use some complex numbers, right? And that integration was indeed a complex integration, sort of, right? So Fourier transform in a way is closely associated with complex analysis, but we shall assume that our knowledge of complex analysis is not that sound, right? If I ask you to do a complex integration, almost all of you, I'm not sure how many of you will be able to actually calculate the complex integration, right? Solve the complex integration. So that way we shall try to avoid complex integration as much as possible, and in order to do that we shall need one very important property of Fourier transform known as the principle of duality. So that is the only property we're going to discuss today, and on the next class we shall be discussing plenty of other properties of Fourier transform that would actually make our lives much easier. And once more I should emphasize that we could have given more emphasis on Fourier series, right? We could have allotted a few more classes on Fourier series. We could have done plenty of other things with Fourier series, but unfortunately for us, I mean, most of the signals that we encounter in our entire course and in real life are not periodic in nature. So studying Fourier series in depth, in huge depth, has its advantages, but also it's not quite relevant with our subject. But Fourier transform, on the other hand, is quite relevant with our subject, because most of the signals are aperiodic in nature, and even if the signal is periodic in nature, you can have a Fourier transform, and Fourier transform has a direct correlation with Fourier series. So in any case, Fourier transform is a superset of Fourier transform. Fourier transform is a superset of Fourier series, right? So whatever you can do with Fourier series can also be done with Fourier transform, right? So Fourier series is inherent within the Fourier transform, and yeah, we actually developed Fourier. We actually showed you developed Fourier transform on as a generalization of Fourier series. So with that said, I believe you can understand that Fourier transform is a more important topic for us. So yeah, so I would hope more people would join, and right. So let's start, right? Let's not waste any more time. Let's start. And again, I would encourage you to interrupt me and ask me a question if you don't understand something, because in this class today, there might be things that you probably won't understand, right? If you don't understand something, before I proceed, please interrupt me and ask me a question on the live chat. With that said, we're going to calculate the Fourier transform for these things. I mean, you are all probably familiar with these signals, and these are quite typical examples on Fourier transform, right? The idea is that if your teacher didn't teach you the Fourier transform of these signals, then probably he or she did a bad job, right, teaching, because these are the most well-known signals that you need to study while discussing, I mean, while having a preliminary course on Fourier transform. Again, this entire Fourier analysis, this topic is a huge topic, and actually you can do way too many things with this. Okay, and we shall have future subjects where we shall discuss Fourier transform in a completely different fashion from a computational point of view, right? So we shall see those things. In any case, before we actually solve anything, let me show you an example. Okay, an example. So let me switch to screen. So again, this is a demo I developed in order to actually explain the Fourier transform better to you. Okay, so right off the bat, if somebody asks you what are the applications of Fourier transform, so let me list a few applications of Fourier transform. Right now you are watching this video, right? Watching this video and listening to whatever I am saying here, right? So throughout this entire process, something is happening which is called compression, right? So the data stream I'm sending from my computer to the YouTube live stream server, okay, takes up about 4 gigabytes, takes up about 2 gigabytes per hour, right? So 1 hour of video uplink from my computer to the YouTube live stream server takes up 2 gigabytes, around 2 gigabytes. So if I take a class of like 2 hours, I have seen that the resulting video that actually gets saved in my computer is about 4.8 gigabytes. You can imagine how big the size of the file is, right? But while so when after I transmit the data stream to YouTube's YouTube streaming server, what happens is they compress the video along with the audio, right? And the video stream that you see, for example, if I'm taking a class of 2 hours, okay, the video stream, if you stream the entire live stream at 720p, okay, the video stream would take about 250 megabytes for entire 2 hour. So which takes 4.8 gigabytes for me, takes only 250 megabytes for you. How is that possible? That's possible through something called compression, right? Audio and video compression. And this is pretty much everywhere, right? Anytime you're listening to something, anytime you're watching something on your phone, on your computer, anywhere, some sort of video and audio compression is happening. And this is one of the most important areas where Fourier transform is used. Okay, so Fourier transform has a very one of the primary applications of Fourier transform is on audio and video compression, right? Not only audio and video compression, image compression, right? So for example, like that. So we cannot really afford to store and stream and send all uncompressed data. We can only afford to store and stream and send and receive data that are compressed. So this, for compression, Fourier transform is what should I say, is indispensable. For example, you cannot get rid of it, okay, for this kind of compression, right? For audio video compression, for example, right? So this is one of the applications, right? The other application is something called analysis of spectrum, for example, right? Sometimes you might have heard what happens is, so sometimes you might have heard that yeah, we know that, right? For example, the environment of Saturn, okay, has these gases. For example, the environment of Jupiter has these gases, right? Something like that. We say things like that, right? Okay, right. But my question is, has anybody ever been to Jupiter? No. Okay. Has anybody ever been to Saturn? No, right? Has anybody ever been to Neptune, for example? Right? No. But we still can say about we can still talk about the environment of those places, right? Of those planets, for example, right? We have even been talking about the environments of exoplanets, okay, right? Planets that are far, far away, really. How is that possible? Have you ever thought about this? How is these things? How are these things possible? Okay, right? So these things are possible by looking at the right light reflected or emitted by those objects, those heavenly objects like the planets and the stars and etc., and doing something called a spectrum analysis on those. Right? So the idea is that different materials have different signatures on the frequency spectrum in the frequency domain. Right? So different signals, the different objects have, or different materials, okay, have different spectrums in the frequency domain, and we shall actually discuss that terminology frequency domain later on, okay, in complete details later on, because that's one of the important criteria here. But Fourier transform takes us from something called the time domain to the frequency domain, and we shall discuss, we shall learn what I mean by that. Okay, so from that we can actually understand what those planets are composed of, right? Something like that. So these are the ideas, for example, right? So and we can study atomic structures from that. And also, for example, I'm talking here, right? So my voice has different frequencies, for example, right? Different frequencies. Now question is, how do you distinguish my voice? So of course, if I'm talking, you people already might be familiar with my voice, right? Okay, because you have listened to it many times, right? Yeah. So how do you recognize a certain person's voice? Okay, your brain inherently does something called a frequency analysis, and it realizes that these are the frequencies, these are the major frequencies that are present in that particular signal. And from that, you can actually distinguish the speakers, right? The people that are talking, right? So those things do happen, really. So with that said, let me show you a very simple example where Fourier transform can be used for frequency analysis, for spectrum analysis, most importantly, right? For example, I'm talking through this microphone and I'm using something called a denoiser, okay, in my microphone, in OBS, which I use to stream on YouTube, right? So I'm using something called a denoiser. What does it do? It denoises signal. So it removes noise as far as practicable. What kind of noise? Noises that are regular in nature, that are quite predictable in nature. For example, so a fan is going on, a fan is running, for example, okay, and when a fan is running, it has a very predictable noise that it introduces in the microphone, right? And the denoiser tries to eliminate that particular noise. And again, who is helping? Fourier transform. So yes, in reality, Fourier transform is pretty much everywhere, even if you know it, right? And let me tell you a very interesting thing about Fourier transform is that if you are trying to multiply or divide two large numbers, for example, okay, so if I give you two large numbers, and by large I mean like now numbers that have millions of digits, for example, okay, and if I ask you to divide those two numbers or multiply those two numbers, okay, instead of directly multiplying or directly dividing them, if you calculate the Fourier transform for those in a certain way, okay, and then by means of the Fourier transform, if you do the multiplication or division, in reality that becomes a computationally easier process than directly multiplying or dividing two numbers, for example, okay. And this is pretty much used everywhere where you study prime numbers, for example, okay, you are factoring huge numbers, for example. In those cases, Fourier transform is an essential tool. So with that said, Fourier transform has applications where you won't probably even imagine that it has an application, for example, right? In the domain of quantum mechanics, Fourier transform is ubiquitous. Wherever there is wherever we are trying to analyze a waveform or analyze a signal, Fourier transform is pretty much everywhere, right? So you might have seen frequency spectrums, right? Of all those spectrums, right? All those graphic visualizers whenever you are listening to an audio or something. Okay, that also uses Fourier transform. In any case, let me show you an example. Okay, I shall send you the file as usual. Right. Okay, again, this is the digital version of the Fourier transform. Of course, since we are using a computer to do Fourier transform, of course, we have to convert everything into digital versions of those, right? We cannot deal with analog versions because computers are very bad at doing analog computation. This is something called a discrete Fourier transform, DFT, right? Now, the idea is same. Okay, so look at this one. Look at this one. What do I have here? What do I have here? I have a signal, right? A pure sinusoidal signal of 50 hertz, right? So try to understand the idea behind this. So I have a pure sinusoidal signal of 50 hertz, right? And if I give you a pure sinusoidal signal of 50 hertz, and if I ask you, okay, tell me what is the frequency? Of course, now what you can do, you can take measurements on the signal and how many cycles it repeats after a certain period of time, and based on that you can calculate the frequency of the signal, right? As long as it's a pure signal, right? It's a pure sinusoid, and you can clearly see the repetitions that is happening, right? So it's a pure sinusoid of 50 hertz. Okay, but what is the best way of calculating the frequency? The best way of calculating the frequency is to actually calculate something called the Fourier transform, for example, here, right? So again, Fourier transform, the expression that we get x omega is a complex expression, and if we take the magnitude, what we get is called the amplitude spectrum. Okay, we shall discuss those terms, don't worry. So we get the amplitude spectrum. So for example, look at what we have here. So we have a signal which is a pure sinusoid, okay, and we have taken the amplitude spectrum of that, and again it's a digital version of the Fourier transform. So yeah, let's keep that in mind. Okay, and digital, whenever you digitize something, it introduces some kind of errors anyway, and these are those errors. But the important point to look at is this. So in the Fourier transform, if I plot this, so this is the Fourier transform, right? Amplitude version of the Fourier transform. So take the Fourier transform and take a mod on that, right? So if I plot the Fourier transform, what do I see? I see almost zero values everywhere, but at 50 hertz frequency, so this is frequency, at 50 hertz frequency in Fourier transform, what do I see? I see a peak that kind of looks like an impulse, okay, and it has a magnitude of 1. So right off the bat, that tells you that this signal was a signal that had a frequency of 50 hertz and an amplitude of 1. So Fourier transform immediately tells you about the composition of the signal, right? Just as an example, okay, and again, this program does not do any dirty trick. This actually calculates the Fourier transform. Yeah, this actually calculates the Fourier transform and plots that. That is what it does, right? So, so look at the signal. So the signal is a pure sinusoid of 50 hertz, and look at the Fourier transform. The Fourier transform tells you that yes, the signal has a 50 hertz component, 50 hertz sinusoidal component that has an amplitude of 1, and that is the entire idea of Fourier transform, right? And Fourier series, as a matter of fact, to figuring out the components in constituent components of signals, right? So with that said, if I increase the frequency, maybe if I make it 100 hertz, now this signal is a pure sinusoid of 100 hertz, right? And what about the Fourier transform? As you can see, the Fourier transform is now telling me that this signal that I have depicted over here has a pure sinusoidal frequency of 100 hertz. And what is the amplitude? Amplitude is 1. So there is no problem with that. Let's increase that even further. Let's make that 150, right? Right, 150. Same thing. So it's a pure sinusoid of 150 hertz. And what about the amplitude spectrum? Yes, in the amplitude spectrum, I can see the Fourier transform actually tells me that this signal has a 150 hertz component in it, and the amplitude of the 150 hertz component is 1. That is what it tells me, right? And that's fine and all, right? We can actually measure these things by hand, for example, if I really need that. But what if this signal is pretty noisy, right? What if this signal is pretty noisy? Okay, in order to depict the noise, let me dial this back so that actually the noise is depicted better. Right. So again, let's go back to a 50 hertz sinusoid, right? And what if I introduce noise to the signal like this? Right. So I've introduced a huge amount of noise in the signal, right? Let's dial back the noise. That was literally a little too huge, right? Right. So I have introduced a lot of noise in the signal, right? Now what do I have? I literally have something called a signal corrupted with zero mean random noise. There are several kinds of random noises, but yeah, this is one of the random noises, which is called a Gaussian noise or a white noise. Okay. So, and again, we shall later on discuss what a white noise is. Okay. But the thing is, yeah, we have just introduced noise in the signal. Okay, this was the original signal. Look carefully. If I get rid of all the noise, right, this was the original signal, but we have introduced a lot of noise in the signal, right? Now the moment I introduce such kind of a noise in a signal, what happens? The signal that I'm dealing with, namely this one, is no longer periodic, right? Of course, noise cannot be periodic, otherwise it's not even a noise, right? So noise cannot be periodic. It's kind of a what should I say, statistical thing, right? So yes, so this signal is no longer periodic, and if I now ask you, okay, take a ruler and a compass or whatever and figure out the period of this signal, yeah, of course you cannot do that, right? Because this signal is aperiodic. You cannot see any proper repetition. Yeah, you can kind of follow a repetition here, but yes, I mean, not very useful. But if I want to figure out what was the underlying signal in it, right? Again, what is the definition of a signal? Signal is a waveform that carries some information. This noise is not carrying any information. Okay, what was carrying information? That particular sinusoid, right? That particular sinusoid was carrying certain information, right? Now it has been corrupted with noise. But if I want to figure out what was the signal present in it, okay, then what do I need to do? I again need to do something called the Fourier transform. Now again, look at the Fourier transform. While before, in the Fourier transform plot here, okay, this is again the amplitude version, so basically taking a mod, right? You're not plotting the phase here, just plotting the amplitude. So while before we had 0 everywhere, okay, for other frequencies, and only a peak at 50 Hz, now we have non-zero values everywhere, which tells me that I have introduced many different compositing signals here, okay, many different compositions with different amplitudes here. But the important thing to note is that out of everything, one peak is very prominent. One peak is very prominent, and which is at 50 Hz. So this Fourier transform plot essentially tells me that even though there are plenty of frequencies, many different frequencies, okay, present in this signal, one frequency is pretty prominent, and that frequency is 50 Hz. And what is the amplitude of that? Approximately 1. So with that said, you can understand by now is that Fourier transform can actually figure out the frequency constituent components present in the signal, right? Fourier transform can actually figure out what are the different frequency components present in the signal and what are their relative strength. Now, if I change the frequency of the signal, for example, to 100 Hz, to 100 Hz, look at 100, right? So this is the 100 Hz pure 100 Hz sinusoid corrupted with random noise, right? And again, see, look at the peak of the Fourier transform. That essentially tells you that this signal has an internal composition of many different sinusoids which appeared because of the noise we introduced, okay? But inherently, this signal has a pure sinusoid at 100 Hz, and that has an amplitude of about 1. That is what it tells me, right? So with that said, if I can design a filter that filters out everything other than that particular frequency, I will get to see that particular signal. So that is how, in order to design filters, we actually use Fourier transform once again, right? So with that said, Fourier transform is pretty much everywhere, right? Even if you don't see it, it's still there. So that is the idea, right? And what we are doing essentially, this signal here, this presentation, this signal is in time domain, right? So this is with respect to time. As time goes on, this is what the behavior of the signal appears to us, right? As time goes on, again, we human beings, we live in time domain, right? But the thing is, we feel in frequency domain. We shall discuss that later on. Yeah. So we do live in time domain, for example. So as time passes for the signal, this is the behavior of the signal. That is how the signal fluctuates, right? But in the frequency domain, so if we calculate the Fourier transform of the signal in the frequency domain, we actually get to see the behavior of the signal. What are the internal components present in the signal? That is what we get to see. And again, this idea would be pretty important for us, because again, earlier I told you in an earlier class that if we can get the impulse response of a system, of a linear time invariant system, we essentially have encapsulated the entire behavior of the system, right? So, and how is that even possible? That will be evident through Fourier transform. So we shall discuss those. So I hope that this initial discussion was good for you. I hope you understood things. Okay, let me just get rid of this, right? So with that said, let's start doing our Fourier analysis. So let's start, right? Fourier transform. So we are solving problems on Fourier transform. And so again, if you have any query, please feel free to ask, right? So before we can start, so let's recall this was our Fourier transform pair. So if so we did this in yesterday's class. If xt is a signal, and again try to understand that for in order for a Fourier transform to exist, the signal could be periodic, could be aperiodic, right? It does not need to be aperiodic specifically, or does not need to be periodic specifically, right? It can be periodic, it can be aperiodic. But if xt is a signal that satisfies the Dirichlet conditions, then the Fourier transform pair for xt is, or rather can be, given by, so this is the expression for Fourier transform. So this is like calculating the Fourier coefficients. Again, we discussed this in the last class. Okay, right? And this is the inverse Fourier transform that gets you the signal back, right? This was like the original summation in Fourier series, and this was like calculating the Fourier coefficients. Okay, this is 1 by 2 pi integration from minus infinity to infinity x omega e to the power j omega t d omega, right? So this is the Fourier transform. And this is the inverse Fourier transform. Right. So that's the expression that we are going to use, right? So, right, let's start our discussion. So I believe, again, I'm telling you, if you have any query during the class, feel free to ask. Feel free to interrupt me and ask. Right. So again, what are the list of problems? Yeah, let's start calculating a few simple Fourier transform. And again, before I need principle of duality, I shall tell you about principle of duality, so don't worry. So we are calculating the Fourier transform of this signal, right? Okay, let's start with this signal, principle of duality, the Fourier transform for delta t, right? Okay, right, let's start with that. So let's start with that particular example, right? So we are calculating the Fourier transform of this. And again, just before I proceed, there is a notation we use often. Okay, there is a notation, particular notation used in electrical engineering. This is the notation used. So we often use a double-sided arrow in order to represent something like the Fourier transform. So we use this expression, right? So if x is a signal, then if we introduce this double-sided arrow, okay, then we say that on the right hand side we have the Fourier transform, on the left hand side we have the original signal, right? So something like that. So the Fourier transform of xt is x omega, and the Fourier transform of x omega is xt. Yeah, we use this notation quite often. So it's better for me to introduce that notation for you. Okay, so okay, let's start with the example 1 that we actually said. So we are calculating the Fourier transform of e to the power minus at ut. Let's start with that. So calculating the Fourier transform of e to the power at ut, right? So this is the notation often again we use. We sometimes write this stylistic f and then the signal we have, something like that. So we are asking for you to calculate the Fourier transform, and this is quite similar to asking you this. This is the Laplace transform. I mean notation for Laplace transform, right? So we are asking you to calculate the Fourier transform, and yeah, for this particular signal. Right? And again, yeah, there are conditions, right? For this signal, I am explicitly putting up a condition, and which condition? This condition, where a is greater than 0. Of course, you can understand unless a is greater than 0, this signal is unbounded, right? And we discussed this while discussing power and energy signals, right? So we discussed that. So yeah, so let's look at the signal. Okay, let's look at the signal. So let's look at the signal. So for this particular signal, what does it look like? Let's bring this back here. Right. Right. So what does this signal look like? So this is my xt, for example. This is xt, right? And we are calculating x omega, trying to figure out what are the frequency components present in it. Again, this is not a periodic signal, right? So with that said, this signal would probably, of course, just because we have ut, this signal would be 0 before t is equal to 0. So this signal would be 0 here, okay? And after t equal to 0, at t equal to 0, the value of the signal would be e to the power 0, which is 1, and ut, which is again 1. So it starts with a value of 1. So at t equal to 0, the signal jumps to a value of 1, and after that it gradually decays with an exponential decay, so-called exponential decay, right? Let me try my best. Yeah, okay, that was my best drawing here. So it is e to the power minus at ut, and this value is a 1. This is t equal to 0, and this is xt, of course. Yeah, this is the signal we are talking about. We are trying to figure out what frequency components it has. Again, it does not have any fundamental frequency, because with that the idea of fundamental frequency was kind of obliterated in the last discussion where we discussed aperiodic signal. This is an aperiodic signal, right? So instead of having discrete frequencies, different particular frequency components, right, it would have a whole spectrum of frequencies, right? The frequency, okay, it won't have any it won't have discrete sinusoidal components, right, that you can individually segregate, but it would have a continuous plethora of sinusoidal components, right? So let's figure that out. So we are trying to calculate the Fourier transform of this. So we are calculating x omega. We are trying to figure out what Fourier coefficients it has, right? X omega is again the Fourier coefficient, for example, the Fourier transform in particular, where omega is no longer discrete in nature. We are not considering n omega naught. We have a continuous spectrum of frequencies. So let's try doing that. So let's start with the first principle. So from definition. So of course, from definition, this is the definition of Fourier transform, right? That's the definition of Fourier transform. So let's put that. So I have this. I have e to the power minus at ut, and then I have e to the power minus j omega t dt. That's the expression for Fourier transform, for example, here, right? So yes, so let's try calculating that. So but before I can calculate this, try to figure out what is the role of ut. The role of ut is to make the signal causal, which means since I have ut multiplied with the signal, that signal has a value of 0 before t equal to 0, right? This signal has a value of 0 before t equal to 0, just because we have ut multiplied with the signal. right? So this integration essentially becomes this. The lower limit automatically drops to 0 from minus infinity, right? And I have e to the power minus at, and there is no point keeping ut here because ut has served its purpose, right? Right. So, right. So let's simplify this. So from 0 to infinity, and I can combine these two. I can combine these two in a way. So I can take minus sign common out of these, and I can take I think t out of these, right? So a plus j omega, and I have t here, and I have dt here, right? I've taken too many things common out of these. Right. With that said, of course, this is like e to the power 80, simple, right? So now we can do the integration and then go ahead for putting the upper limits. So I have e to the power minus a plus j omega t divided by minus a plus j omega, and the lower limit is 0, upper limit is infinity. Again, if you have any query, please feel free to post them on the live stream. Yeah, someone asks where is ut. Of course, ut is, what was the purpose of ut? The purpose of ut was to make sure that this signal has a value of 0 before t equal to 0, right? Otherwise, e to the power minus 80 would have looked somewhat like this. It would have started from here, like with a minus infinity, from a huge value, right? And would have gone down like that. But since I have ut multiplied with the signal, what happens? This signal has a value of 0 before t equal to 0, right? So as long as t is negative, this signal has a value of 0 because ut has been multiplied with the signal. And from here to here, ut has served its purpose. What was the purpose? The purpose was to make sure that the lower limit boils down to 0. Because try to understand, when we are integrating from minus infinity to plus infinity, for the entire span from minus infinity to 0, this ut is 0. So this entire integral is 0. So I do not need to integrate from minus infinity to plus infinity. I can just do the integration from 0 to infinity. Just because ut has a value of 0 before t equal to 0. So from here to here, I have omitted ut because I have considered the lower limit to be 0. Because ut has now served its purpose. What was the purpose? The purpose of ut was to make sure that the signal has a value of 0 before t equal to 0. And that is what it has done, right? And this purpose is particularly known as making a signal turn into a causal signal. So this is a causal signal, of course. This signal has a 0 value as long as t is negative. Okay, and this is what ut has done. So this is where ut has gone actually. Okay, ut has made sure, so value of ut when t is greater than 0 is 1, and value of ut when t is less than 0 is 0, right? So we are not considering the points where t is less than 0. So we are actually integrating from 0 to infinity, right? So I believe you people got that, right? Again, if you have any query, feel free to ask, because don't just assume anything. Okay, right? Let's put the upper limit and lower limit, right? Now when we are putting the upper limit, there is a very important assumption. What is the assumption? So we are putting e to the power, yeah, and then in place of t we are putting the infinite limit, right? Positive infinity we are putting, right? And inherently in our mind we are probably assuming, okay, right, this is e to the power minus a infinity, right? Something like that. But again, see that, and of course some of you might think that, okay, that boils down to 0, right? I have e to the power minus infinity on top, right? But that assumption is correct if a is positive, right? If a is positive only, that assumption is correct. Otherwise this assumption is not correct. Let me just show you what I mean by that. So we are trying to put an upper limit, right? We are calculating this limit t. Okay, this is the side discussion, so let's do it on side. So we are trying to calculate this right now. Limit t tending to infinity, e to the power minus a plus j omega t. We are calculating this limit, right? So for the upper limit, so that's fine, right? So let's expand this. So e to the power minus at into e to the power minus j omega t. So e to the power minus at into e to the power minus j omega t. So with that said, limit t tending to infinity. Here I have e to the power minus at, and what is e to the power minus j omega t? It's nothing but cos omega t minus j sine omega t. I believe you people are already quite familiar with this. Now this is a pure sinusoid, right? This is a complex sinusoid, but this value cannot go beyond plus 1 minus 1. Again, this value particularly cannot go beyond plus 1 minus 1. So this entire complex number present in here, okay, cannot go beyond 1 plus j1 and minus 1 minus j1. It will vary between those two values, right? It cannot go beyond that. So this is a quite finite quantity. This quantity is finite. So whatever you put in place of omega and t, this value cannot go beyond plus 1 plus j1 and minus 1 minus j1, right? It cannot go beyond that. So it's a finite quantity, but this is not necessarily so. So if we put t tending to infinity, this reduces to 0 only if and only if a is ensured to be greater than 0. Okay, a is a real number I am considering. So if a is greater than 0, then only we have e to the power minus infinity on top, right? And then only this actually boils down to 0. So that's one of the conditions that we have placed here, right? So I believe, yeah, that's understood, right? So with that said, and if a is somehow negative here, okay, yes, we have a problem then. If a is negative, then what is the problem we have? The problem we have is that if I put infinity here, and a is a negative quantity, then we get essentially get e to the power infinity. So that way it becomes a positive quantity, e to the power positive infinity, and that's infinity, right? So the limit won't exist, right? So with that said, the upper limit of this integration here, the upper limit of this integration is 0, and then minus, when I put the lower limit, that's quite understandable. So when I put the lower limit, I have minus a plus j omega on bottom here, and that's 1, right? E to the power 0, right? Again, that was a side discussion, right? So that's 1 by a plus j omega. That's understood, I believe, right? So what did we just discover? We discovered that the Fourier transform of e to the power minus at ut was 1 by a plus j omega, right? Right. So let's try to figure out what frequency components this signal does have, right? So we have figured out that the Fourier transform is 1 by a plus j omega. Then what is the magnitude of that? It's a complex number, so let's calculate the magnitude. Of course, the magnitude for complex numbers, if we have a ratio, then the magnitude or modulus of the complex number can be calculated as individual moduli of the numerator and the denominator. So I have mod a plus j omega, and that gives you 1 by root over a square plus omega square, right? I believe so. So with that said, if I now try to figure out what frequency component this signal does have, that would be the result. Let me show you. For that particular example, right? And if I draw the signal, for example, here, draw this integration, I mean draw this Fourier transform magnitude here. Okay, apparently I am very bad at drawing. What am I doing? And this is not t, huh? This is omega. So what does this tell you? This essentially tells you that this signal has plenty of frequency components. Okay, in fact all possible frequencies are present within the signal, right? And for example, and again when and this has a value, when omega is 0, this has a value of 1 by a. When omega is 0, this has a value of 1 by a, right? So now if I ask you this, what is the DC component present in the signal? Okay, of course the idea is that it came from Fourier series, right? I can ask you what is the DC component present in the signal. What is the DC component present in the signal, right? If I ask you that, your answer would be pretty simple. What is a DC component? DC component is the zero frequency component, right? What is the DC component? DC component is the zero frequency component. And if I ask you what is the DC component, what is the amplitude of the DC component present in this signal? Okay, what is the amplitude of the DC component present in the signal? The DC component is of course the zero frequency component. Now this is the frequency spectrum for that particular signal. Again, the drawing was pretty bad. I'm unsatisfied with the drawing. Much better, right? So yeah, so if I ask you what is the DC component present in the signal, you just have to look for the zero frequency component, and at frequency 0, what is the amplitude of the amplitude spectrum? So this is the amplitude spectrum, often called the amplitude spectrum, right? Amplitude of the Fourier transform, just like we have shown you earlier, right? For the noisy signal we are plotting this amplitude spectrum only, right? Now this signal has different components. Now at zero frequency, here what is the amplitude is 1 by A. So I can happily say that this signal has a DC component equivalent to 1 by A. This signal has a DC component which has an amplitude of 1 by A. Okay, I have actually drawn this because I know how to draw this. Okay, you can use a calculator, and I shall teach you later on how to draw these kind of things. But you can take a calculator, okay, fix a certain value for A, okay, certain positive value for A, and put different values of omega. You will see this plot, okay. Or you can use a computer program, for example Python, to actually plot this. Okay, this is a plot of this, nothing else, right? So from that plot, okay, like we have shown you a demo, right? A Python based demo where we had a signal which was a noisy signal, and we did plot the frequency spectrum, amplitude spectrum, and this is the amplitude spectrum for this particular signal, right? For this exponentially decaying signal. Now if I ask you what is the DC component for this present in the signal, you can tell me that the DC component, which is the zero frequency component, has an amplitude of 1 by A. Okay, that's understood. Now if I similarly ask you, okay, tell me what is the 1 hertz, what is the amplitude of the 1 hertz component, 1 radian per second component, you can simply go ahead and figure out where omega is equal to 1 and subsequently calculate the magnitude. And from that, now you can tell me, okay, the 1 radian per second component has this much amplitude, has this much amplitude, for example, right? What is the amplitude of the 1.5 hertz component, 5 radian per second component? So that's 1.5, say. Okay, you can tell me, okay, this is the amplitude of the 1.5 radian per second component present in the signal. But unlike periodic signals, all the intermediate frequencies are also available, right? Now if I ask you what is the next frequency after 1 radian per second present in the signal, okay, it is not like the concept of harmonics, right? Earlier in our earlier Fourier series examples, we had a fundamental frequency, and every other frequency was just a multiple of the fundamental frequency, namely a harmonic. But here all intermediate frequency is available. All intermediate frequencies are available because frequency is a continuous term here, right? So there are infinitely many sinusoidal components between any interval you might want to choose, right? So basically all frequencies are available here, and that is the signature of the frequency response for that particular decaying signal, right? Right. So that is what the Fourier transform actually tells you. It tells you the frequency composition, right? And this is what brings you the frequency domain analysis. Now, instead of looking at the signal in the time domain, how it changes with respect to time, okay, we are looking at the signal in frequency domain. We are trying to figure out what are the constituent components present in the signal. What does make the signal itself? We are not looking into how the signal changes over time. We are looking into what the signal is composed of, what it is made of in terms of frequencies in sinusoid, frequencies of sinusoids, right? And again, as long as the signal satisfies Dirichlet conditions, it can be always expressed as a composition of sinusoids because the Dirichlet conditions were sufficient conditions, right? So that's our example 1. Okay, I believe all of you have got this far. Okay, let's go into example 2. What was our example 2? Yeah, e to the power minus a mod t. So I'm solving all the what should I say, all the standard problems on this. E to the power minus a mod t, right? Well, I don't need to put ut here. This signal does not need to be causal for this particular example, and a is greater than 0, right? So before I can proceed with this, I need to be able to express this. So let's express this, right? Okay, you understand the way modulus works, right? I have mod t. Mod t is something like this. It's plus t as long as t is greater than 0 or greater than equal to 0, say, and it's minus t as long as it's and t is less than 0, right? And of course, when t is equal to 0, it's 0. So yes, I can put the equal to sign anywhere I want. Any of these, and putting an equal to sign any one of these is sufficient, right? So for example, if I put minus 5 here, I get a minus of minus 5, so it's a plus 5, right? So with that said, how do I express this particular signal? I again have to express this in a piecewise fashion. So I have to express in these two particular order. So when t is less than 0, something would be happening, and when t is greater than equal to 0, something would be happening, right? So when t is less than 0, of course I have an additional minus sign because of this t. So I have e to the power at, and when t is greater than 0, I don't have any additional minus sign, so I have e to the power minus at. So that is the expression for the particular signal. So let's draw it first, and then we shall discuss. So let's first try to draw it in the time domain. So what it looks like in the time domain. Okay, how it varies with respect to time. Let's first inquire that, and then we shall actually see how it varies in terms of frequency. So it is in time domain now. And of course, if I draw this signal, of course, at t equal to 0, the value of the signal is 1. After that, it decays exponentially, right? It exponentially decays. And before t equal to 0, again, I have a negative value for t. Okay, and again, that will be an exponential decay on the other side. So this signal is a very weird one, where the maximum value that signal ever reaches is equal to 1, and it decays in both ways, in both directions. Okay, it decays in this direction. Okay, bad drawing. Again, bad drawing. I should really be able to figure out a way of drawing this without exhausting myself. And that is how it decays in this direction. And that is how it decays in this direction. So basically, as long as t is positive, right, and there is a sharp point here, right? Anyway, my idea is that when t is positive, this signal decays like e to the power minus at, and when t is negative, this signal decays as e to the power at, right? So we have this kind of a signal, right? And now we are trying to figure out the frequency components present in it. So this is how the signal varies with respect to time, and this is no longer a causal signal because I don't have ut multiplied with the signal, right? So when t is less than 0, the signal does have some value other than 0. So let's calculate the Fourier transform. So what is the Fourier transform? So we are calculating x omega, which is the Fourier transform. Again, recall the capital X, right? So we have from minus infinity to infinity. And again, just to tell you that I am not going to pull a 2.5 hour class here. Okay, so yeah, I shall be doing it for like 1 hour 40 minutes at max. So if we still have unsolved problems at the end of today's class, we shall continue that on the next class, right? We are not in a hurry, right? So with that said, that's the integration, and we are doing it on the signal, right? So e to the power minus a mod t, and then e to the power minus j omega t. So that's xt. This is xt dt. And again, the assumption here is that a is greater than 0, right? Unless a is greater than 0, none of these would decay, right? So we have this expression, and this integration can be now split into two portions, one from minus infinity to 0. So when t is negative, essentially when t is negative, we already know that when t is negative, this is the expression for e to the power mod at, right? E to the power mod at. So right, so with that said, it would be e to the power at e to the power minus j omega t dt, and when t is positive, I have 0 to infinity e to the power minus at e to the power minus j omega t dt. So I don't think there is any issue with that. So let's multiply these. So I have e to the power, and let me take a minus j omega common out of these, and here I have 0 to infinity e to the power minus, I have a plus j omega common out of these, right? So I have split into two portions here according to the piecewise definition. And again, just for your attendance, because in the last class something weird happened. I mean, few of you attended the class but did not write anything on the live chat. So for your attendance, okay, write anything. Even if you don't want to ask a question, write something, okay, so that I get to see your name here, so that I can get to give you the attendance, right? Okay, it's going to be yeah, 0 0, right, you people are following, right? So right, so let's integrate that. If I integrate that, so e to the power a minus j omega t by a minus j omega, yeah, it makes me happy when you can figure out the errors I make, because that tells me that you are actually following things, or rather you are actually able to follow things, right? Okay, what am I doing here? Hold on. Right, so those are the two individual integrations, right? Okay, right. So with that said, let's put the upper limit here. If I put the upper limit here, I have e to the power 0, that's 1, and lower limit. Now if I put minus infinity here, try to recall that a is a positive quantity, and since a is a positive quantity, I now have e to the power a negative quantity, e to the power negative infinity, since a is a positive quantity, and e to the power minus j omega is just a sinusoid, right? Yes, I think your answer is correct. Right. So if I put minus infinity, the result is 0, of course. And similarly, if I put plus infinity, it's 0. And if I put 0, I have minus, another minus sign, a plus j omega, and on top I have 1. Right. So no. Someone is asking, sir, will a always be greater than j omega? No. A does not have to be greater than j omega, because a is a real number, j omega is a complex number, and the concept of equality and inequality, saying greater or less, is not applicable for complex numbers. What I'm saying, look at this one. How did we consider this limit? Did I ever say a was greater than j omega? No. Or a was greater than minus j omega? No. Because this j omega is making a sinusoidal component which is finite in nature, right? So the limit has nothing to do really with j omega. It has everything to do with a, right? So here again, if I put the limit here, try to understand, this becomes e to the power at into e to the power minus j omega t. And what is e to the power minus j omega t? E to the power minus j omega t is cos omega t. So cos omega t minus j sine omega t. So that's a finite quantity. And with that finite quantity, we have multiplied e to the power at. And that is where the limit is actually affecting the most, right? Because with e to the power minus j omega t, that's just cos omega t minus j sine omega t. And whatever value you might want to put in place of omega and t, cos omega t minus j sine omega t can vary from -1 minus j1 to +1 plus j1. It cannot go beyond any of these. So that's a finite quantity. But e to the power at, which is multiplied with that cosine sine term, okay, that can go to infinity. That can become 0. Things like that would happen to it, right? Based on the value of a. A is a real number here. Okay. And again, for two complex numbers, say z1 and z2, they can be equal, but this kind of implications are invalid, particularly invalid, right? For complex numbers, you cannot say one number is greater than other, one number is less than other, something like that. This is called Archimedean equality. Archimedean equality. So yeah, those kind of inequalities, those kind of Archimedean ordering. This is not an Archimedean ordering. This kind of ordering is not valid in complex numbers. Like you cannot say one complex number is greater than the other. That's not true. That's not actually applicable in mathematics. So I have 1 by a minus j omega plus 1 by a plus j omega. And subsequently, if I just add these two up, I get, of course, in the denominator, I get a minus j omega into a plus j omega, which is a square minus j omega whole square. Again, j square is equal to -1. So we essentially have a square plus omega square. And on the numerator, if I just add these two, I have 2a. And surprisingly for us, this gives me a very similar expression. So if I want to calculate the amplitude here, that's going to be without a doubt 2a, because this is no longer a complex number, it's a real number for all intents and purposes, right? Not like the previous example. So here, if I want to look at the signal from the perspective of frequency, so it's omega, and this is mod x omega, right? If I want to look at the signal from the perspective of frequency, again, I know how to draw this because I know how to draw this. Okay, the drawing would be pretty similar to the one we had actually drawn earlier. Okay, pretty similar in many ways, right? Only slightly the slope would be slightly sharper based on the value of a. Okay, and this particular value, the peak it ever reaches, has the value of course, when omega is equal to 0, the peak is reached, and when omega is equal to 0, the value is 2 by a, I think, 2 by a. Right, this is zero frequency component. So again, if I ask you what is the, again, I'm going to tell you how to actually draw these things in using Python. So we shall shortly have, in a few days, we shall have a class on, we shall have a very quick discussion on Python, and we already had some discussion on Python. I shall teach you how to actually use Python to effectively do this kind of computations, right? To plot things. I mean, right? So how to use Python as a calculator on steroids. So again, if somebody asks you what is the DC component present in this signal? Okay, what is the DC component present in this signal? From the Fourier transform, you can essentially tell that, okay, the DC component, which is the zero frequency component, has an amplitude of 2 by a, and the amplitude of the successive sinusoidal components eventually decay, right? Decay. Right, so on. Right, so I believe you got that far, right? Again, we are completely skipping the phase term because it's a complex number. These things are complex numbers, and whenever we are dealing with complex number, we have an amplitude and a phase, right? We are skipping the phase terminology completely here, because we shall be talking about phase later on after we have discussed systems on its entirety. Otherwise the idea of phase won't be that useful for you to understand. Okay, the realization of phase won't be any useful. All right, what is the third example? All right, delta t, really my favorite signal, and there would be quite a few implications for delta t. Okay, so before I can actually proceed with delta t, recall we that in our actually regular physical classes we discussed about delta t. And one more thing, if you think I need to we need to recap some topics we discussed in our earlier classes, feel free to send me a mail. I can arrange some classes that we shall be using for recapitulating our earlier classes, right? So if you have forgotten something, if you want to recall something, then please let me know. Okay, and we recall in this particular example we discussed about, and I said one of the most important signals in the entire signals and systems and entire signal analysis spectrum, okay, is the Dirac delta or the unit impulse signal, right? And it has plenty of interesting properties. One of the most important properties of the unit impulse signal delta t was this integration ft delta t dt was f0 as long as ft as long as ft is continuous at t equal to 0. So with that said, this was one of the most important properties that we actually proved in one of our earlier classes, or earlier physical classes, right? So recall that. We have to keep that in mind. With that said, we are now calculating the Fourier transform of so now xt is delta t. We are calculating the Fourier transform of this, and you shall soon realize that this has huge implications. What huge? Let's see. When I say huge implication, it actually has a lot of implications in signal processing. So this is the signal for which we are calculating the Fourier transform, right? Let's apply the definition. Of course, now we have delta t and e to the power minus j omega t. Right, now we are at it. I believe I won't be able to end this discussion today entirely, the entire discussion. So we shall need 2 more classes on Fourier transform. In any case, that'll be good for you and good for me. Right. Now, I mean, we do not need to solve this integration at all. We just have to figure out that this formula is directly applicable here, because we have delta t, right? We have delta t, and this is my ft, right? This is delta t, this is ft. This is just like this formula or this property of delta t, right? This property of delta t. So this property of delta t. So look at this one very carefully. So this is ft and this is ft here, and this is delta t, this is delta t. So the answer would be f0. What is ft? Ft is e to the power minus j omega t. What is f0? E to the power minus j omega into 0, right? Right. So in place of t, I am putting 0. So yeah, right. So this becomes e to the power minus j omega into 0. That gives me 1. So the Fourier transform of delta t is equal to 1, right? And again, please let me know if you haven't understood this integration, because it has huge implications in signal analysis. So what have we just discussed? We have discussed Okay, this one, right. So this integration, right? So I believe this, you have to assume this property right now, because I cannot prove this property right now. That takes me like 20 minutes to prove this, maybe 15 minutes to prove this property, and we did that in an earlier physical class, right? But this is one of the fundamental properties of Dirac delta, or impulse, unit impulse. Now in this example, we are doing a similar integration from minus infinity to plus infinity on delta t ft delta t, right? So here we are assuming that this portion is ft. So we have ft into delta t, like just like that. So the result would be simply f0 because of this property. And what is f0? f0 is, this is ft, right? In place of t I am putting 0, so I have e to the power 0, so I have 1. And this is again the definition, from the definition of Fourier transform, right? X omega is integration xt e to the power minus j omega t dt from minus infinity to plus infinity. That's the definition of Fourier transform, right? And we are solving this particular integration by means of a property of the unit impulse signal. So is that understood? Right. All right. So if you have any other doubt, please let me know. Please let me know. All right. So let's proceed. So we have just realized that the Fourier transform of delta t is equal to 1, right? So what implication does it have? Or rather, what implications does it have? I should say. So this is t and this is omega, and here I am plotting x omega, the amplitude response, and this is the signal, right? So what was the unit impulse signal? Of course, you know that the unit impulse signal is a signal that has a very small time span, right? That has a very small time span, and we discussed that in the class where we discussed convolution. And this is really why I discuss convolution before going into Fourier transform, because that gives me an opportunity to actually tell you about the mysteries that the unit impulse signal holds, right? So this is the unit impulse signal, and this is how we express the unit impulse signal, right? This is how we express the unit impulse signal. So this signal has a very high amplitude, but it lasts for a very small amount of time in the time domain, right? So essentially, like shooting a gun, for example, like a gunshot. We heard that sound and we discussed that about impulse responses, about impulse signals, for example, with the story in our class on convolutions, right? So that's our impulse signal. Impulse signal essentially is a signal that appears for a very small amount of time, but has a very large amplitude, so much so that the integration under the curve is equal to 1. Okay, so if you integrate an impulse signal, unit impulse, over from minus infinity to plus infinity with respect to t, the result would be equal to 1, right? So its width is so small, but the height is so large that the area is actually still equal to 1. And this is how we discuss things in our earlier classes. So I think impulse is fine. So in terms of time, this lasts a very small amount, right? And has an amplitude of very large amplitude. But what about this one? What does the Fourier transform tell me? The Fourier transform of delta t tells me that it's just a constant value. It's 1, right? 1 throughout. So Fourier transform of delta t simply tells me that the Fourier transform is equal to 1, right? That's the Fourier transform of delta t. But I just said moments ago, it has very, very serious implications. What very serious implications? Now if I ask you, what is the amplitude of the 0 radian per second component or the DC component in delta t? If I ask you this, what is the amplitude of the DC component present in it? Your answer would be 1. Next question, what is the amplitude of 1 radian per second component, 1 radian per second sinusoidal component in it? So you find out 1 and you see, okay, fine. The 1 radian per second component also has an amplitude of 1. If I ask you, what is the amplitude of the 0.1 radian per second component present in it? The answer would still be 1. Okay. And if I ask you, what is the amplitude of the 1000 hertz radian per second component? The answer would be still 1. The answer is always 1, for example here. Okay. And what frequencies does it have? Answer is, it has all the frequencies. Try to understand, it has all the frequencies, because any frequency you want to see, okay, it will still have a value of that composition, okay, that component. And if I ask you what is the frequency of the 1000 hertz component, 1000 radian per second component, what is the amplitude of that? The answer would be 1. So essentially I can tell you this. Therefore I can say delta t can be considered to be such a signal that has every possible, rather I would say later on, that has sinusoids of every possible frequency present in it. Or rather, I would rather try to modify my statement here. Present in it, or rather, importantly, so let this statement sink in for a moment. What this Fourier transform told me is that delta t can be considered to be such a signal that has sinusoids of every possible frequency present in it in the same amount. Right. So, and that's quite amazing, right? So this impulse, unit impulse signal, can be assumed as a composition of every possible sinusoid, every possible frequency. So question is, what frequencies does this unit impulse have? It has every possible frequency. And how much amount? It does not do any discrimination on anybody. It has every possible frequency, the same amount. Okay, it has same amount of every possible frequency component. So now let me ask you a question. What is the impulse response of a system? The impulse response of a system is nothing but when I have a system and I give impulse or unit impulse as an input. But under the hood, what is an impulse signal? An impulse signal is the culmination of every possible frequency that you can ever have. An impulse signal can be assumed to be a combination of every possible frequency that can ever exist. the same amount of every possible frequency that can ever exist. So when you are exciting a system with an impulse signal, you are actually exciting the system with every possible frequency that the system can ever encounter. Let me repeat. So when you excite a system, or rather when you give a system an input of a unit impulse, so when you excite a system with a unit impulse signal, or when you excite a give unit impulse to the input of a system, what are you actually doing? You are, from the perspective of the system, you are exciting the system with every possible frequency that the system might or might not ever encounter. And that is how, mathematically as a fact, the impulse response gives you the output of the system for every possible frequency the system might ever encounter. Again, let that sink in. The impulse response we discussed earlier in the last class while we discussed convolution, I told you very specifically the entire behavior, everything about a linear time invariant system is encapsulated within the impulse response of the system. And this is why, because when you excite a linear time invariant system with an impulse input, you're actually exciting the linear time invariant system with every possible sinusoid that ever exists, and same amount of those. All of those sinusoids are being given to the system all at the same time at the same amount, with the same amount. That is what an impulse is in behavior, in nature. And that is how when a system generates an impulse response, so you give impulse as an input, you get a response of the system, which is known as the impulse response. What is that? The impulse response is how the system behaves to every possible frequency, right? So if you somehow know the behavior of the system at every possible frequency, then you essentially know the entire behavior of the system. That's not a surprise. So that is how things really work. So, and if you understand the mathematics behind this subject, signals and systems, you shall soon try to realize, have a feeling about the subject that this kind of simple mathematics can actually mean many wonderful things for real physical systems, really, right? And this is not just some hypothetical explanation here, right? I gave you real life examples, right? So that is how things really work. And not only that, many other behaviors of the system can also be implied or can also be calculated from the impulse response, right? So there are so many things, and we as human beings, we can also be categorized or understood from our impulse responses, right? If someone makes you angry, and out of an impulse you might do something, or you might say something, right? And what you do and what you say when you get an impulse, okay, suddenly you are enraged and you are saying something or doing something, that tells you about your inner behavior, right? Your internal behavior, right? Yeah, that's true for us as well. So with stories apart, that's the Fourier transform of the Dirac delta or unit impulse. Okay, let's go back. What was our fourth example, right? All right, so fourth example was 1. Before I can do that, let's talk about principle of duality. So if you have any query, please let me know. So now we are discussing something called the principle of duality. Now again, before I can discuss principle of duality, I told you at the onset of the class, today's class, that principle of duality is really needed because we are engineers, right? And we are really bad, potentially bad at complex analysis, right? I was quite bad at complex analysis until I actually took a whole semester class on complex analysis after I graduated. Okay, we did do complex analysis a lot, and after that actually I really understood complex analysis. I don't expect you people to understand complex analysis as a matter of fact, because when I was a student, I was a UG student, I did not understand complex analysis at all, really. Complex integrations, complex differentiations. I mean, I could solve those problems, but I did not really understand how those things actually really work internally. But now I do. In any case, we are trying to avoid complex analysis as much as practicable, and for that this principle of duality would come pretty handy, right? To avoid complex analysis, that is the goal, if that is the goal. So what is the principle of duality? We are saying that if xt has a Fourier transform of x omega, let's try to understand what I just said. I said xt has a Fourier transform of x omega, then what is xt? What is xt? Xt is 1 by 2 pi. So we're writing the expression for, so we're writing a proof. We are proving something that I did not discuss even, right? So what is the inverse Fourier transform? That, right? I'm going to explain this, and then we shall solve a few typical problems. Okay, so we have x omega e to the power j omega t d omega. That's the expression for inverse Fourier transform. And what am I proving? I haven't yet told you, right? So with that said, right, so with that said, if I put x of minus t, with that said, if I put x of minus t, so instead of t, if I say x of minus t, so I'm replacing t with minus t. If I get that, what do I get? 1 by 2 pi integration from minus infinity to infinity x of omega. Again, that's the expression for inverse Fourier transform, IFT, right? And instead of t, I'm writing minus t, so e to the power minus j omega t d omega, right? I don't think there is an issue with that, right? And with that said, let's try to do something crazy here, apparently crazy, but try to understand that in this entire integration, okay, let me just rewrite the whole thing once again. Just copy paste the whole thing once again. Let me just copy paste the whole thing once again, because I'm going to do something. Yeah. Right, I just copy pasted everything. But try to understand that this is sort of a definite integral, right? Where omega is the variable of the integration, right? So instead of saying omega, I can give it any name I want. Instead of saying omega, hold on, right? So instead of saying omega, I can say anything I want. I can say p, for example. I can say p, for example. I can say p here. Is there any problem with that? Of course not, right? Because we're just replacing dummy variables, right? Dummy names, right? Right? Again, t is just a name, right? Placeholder for a variable name, right? I can change the name to anything I want. Say, I can say m, who knows? Take a say. I can say b, I can say m, whatever. I'm writing m. Right. I just change the names. There is no problem with that. There is no mathematical issue with that. Right? Now imagine I did not have this expression. I don't see this. Imagine I don't see this. I only have this expression. Right? There is no problem with that. And again, I can once again change my names. Right? I can, instead of saying p is just a name, I can say t here. No one is going to object because these are just placeholder names, right? Of course, instead of p, I'm saying t here. And once again, instead of m, I can say anything else. I can say cow, I can say donkey, I can say anything. I can also say omega. So I can do that, right? Because these are just names, right? Dummy names, basically. Okay, but we cannot do anything on x, right? I cannot do anything on e. These aren't dummy names, but t, omega, these are just dummy names, right? So we have something like this, something like this. So therefore, what do I have? I'm writing this on the left hand side. Try to understand. I have 1 by 2 pi integration from minus infinity to infinity capital xt e to the power minus j t omega, and omega t are the same, j omega t. We have dt, which is equal to x of minus omega, right? I just interchange everything, which basically means if I take this, which implies if I bring this 2 pi to the right hand side, I would get integration from minus infinity to infinity capital xt e to the power minus j omega t dt as 2 pi x of minus omega, right? But what is this? This is the Fourier transform of capital xt, okay, and this is equal to 2 pi x of minus omega. So we have just proved something, okay, and what have we proved? We have so proved that if, hold on, right, we have proved that if the Fourier transform of xt is capital X omega, then the Fourier transform of capital xt would be 2 pi small x of minus omega. So principle of duality tells if this is so, then this is. And the best way of explaining this would be solving an example. Okay, let me solve an example so that it's actually understandable. So our fourth problem was we were trying to figure out the Fourier transform of 1. Fourier transform of 1. Okay, right? We are calculating the Fourier transform of 1. Right? Fourier transform of 1. So we have 1, right? So xt equal to 1. Now let's try to see how we can actually do this in the standard way. Okay, right, from the formula, from the definition, right? So, and we will shortly see, and this is the difficult way, the complex way rather, the complex way. And in the complex way you have to know complex analysis, right? But I would assume that I don't know complex analysis, so I won't be able to actually solve this in this way. So I'm calculating the Fourier transform of 1. That might seem pretty easy. Let's do that. So from minus infinity to infinity, I am doing this integration minus j omega t dt, this integration. Fine. So I have integration from minus infinity to infinity e to the power minus j omega t dt. Now we have a problem. What problem? The problem is in this, right? If I integrate this, I have e to the power minus j omega t by minus j omega, and I'm putting the limits. But what is e to the power minus j omega t? Again, let me write. It is cos omega t minus j sine omega t minus j omega, and we are placing the limits for these. Now if I put infinity, I'm not entirely sure what value I'm going to get, right? Okay, because I know that cos omega t can vary between plus 1 minus 1, sine omega t can vary between plus 1 minus 1, but I'm not entirely sure what exact value it will end up reaching when I put infinity, and same case for minus infinity, right? So this limit does not exist in this fashion. In fact, this is entirely wrong. This is not how you do this integration. This integration cannot be proceeded this way. This integration cannot be done this way, right? So you have to handle it in the using some properties of complex integration, right? Which we probably do not know, and I don't want to teach you, right? Unnecessarily. So yes, we cannot do that in this way. So let's do it the duality way. Okay. Right. Right. So our objective is again to calculate the Fourier transform of 1, right? But I cannot really do that, right? I cannot really do that from our initial expression here, right? But I have, few moments ago, I have done a very important job. I have calculated the Fourier transform of delta t, which resulted into 1. So I know I can write this now. We know that the Fourier transform of delta t is equal to 1. Now this is my xt, try to understand. This is my xt, this is my capital X omega, right? Now what do I want to find out? I want to find out the Fourier transform of 1. Now I can consider that 1 to be capital X being here, right? So capital X was here, now I have brought capital X here, right? So essentially principle of duality gives me Fourier transform of Fourier transform, for example, right? So I'm assuming that here, right? So what does principle of duality tells me? The principle of duality essentially tells me that if I look back, if I know the Fourier transform of xt to be x omega, then I can go other way around. The Fourier transform of this can be calculated as this. So what I mean is I know that the Fourier transform of delta t is equal to 1. So the Fourier transform of 1 can be calculated as this from the principle of duality, 2 pi x of minus omega, right? Principle of duality told me that. So what is the result? The result is simply 2 pi and x of minus omega essentially means this is xt, so x of minus omega means delta of minus omega, right? Right? There is no problem with that, right? I hope. So Fourier transform of delta t is equal to 1. Then Fourier transform of 1 is 2 pi delta of minus omega from the principle of duality. Because doing this in the complex way would have been really complex for us. But we have, please ask me if I have to repeat this. Because we shall be using duality quite often. This is a very trivial example of duality. Right. So, but we know something very interesting about delta t. We know, again recall certain property of delta t, right? Yeah, please others. Mahesh says okay, it's clear. What about others? Well, I mean, this discussion will be the end of today's class in any case, but we shall resume this class on the next one. We had quite a few problems which we shall leave for the next class, and then on the next To next class, we shall be actually discussing the properties of Fourier transform. Right. So the idea is we are not in a hurry. We don't have to end everything in a single class. Right. With that said, let's recall one of the properties of delta t. Delta t is one of the properties of delta t was that delta at was 1 by, again we proved this in an earlier class. Please let me know. Okay, if the video quality dropped to 140 or 144p in your case, please switch to 720p because the stream quality did not drop. Something happened from your end, maybe your internet connection dropped. Okay, that happens automatically. Switch to 720p manually, I mean, or something like that. Don't keep it to auto. Okay, if you keep it on auto, okay, instead of dropping the entire video, it drops the quality. Okay, maybe your internet connection dropped, and that's quite usual, not unusual. Okay, right? So this is one of the properties of delta t, right? So with that said, I can say, what about, okay, you people know that, right? So if I have delta 2t, then 1 by 2 delta t, it's like that, right? So yeah, 720p is not available on phone, of course, because on phone, due to this current ongoing lockdown, so that we don't break the internet. Yes, on phone 480p is the highest, of course. If you are watching it on a phone, 480p is the highest, because just because we are everyone is sitting sitting at home, we don't break the internet by watching high quality videos, right? That's why on phone you cannot go beyond 480p. That's true for everyone in India and Europe as well. Right, so we know that from that property we discussed earlier. Again, if you need a recap discussion on any of the previous topics, please let me know. So we have delta of minus t. What is delta of minus t? Delta of minus t can be assumed to be delta of minus into t, so minus 1 into t, right? So this is from this property like that, right? So subsequently that's going to be delta t, right? So delta t is an even signal. Dirac delta is an even signal. Okay, right? This impulse is an even signal, right? So moments ago we just discussed that the Fourier transform of 1 is 2 pi delta minus omega. So instead of minus omega, I can say plus omega because that's an even signal. So therefore, the Fourier transform of 1 is 2 pi delta of minus omega, right? Which is equal to 2 pi delta omega, right? Yeah, that's same. Yeah. So let me draw a picture of what I just said. So that's my signal here, right? This is a constant signal, constant at 1, right? And this, so this is a DC signal, right? Which has been forever, there forever, for example, right? This is not a causal signal, this has been there forever, and this is the frequency response for that, omega, and this is mod x omega, right? So this is xt, this is x omega, right? So what do I see? I see an impulse. And what is the area of the impulse? This particular area of the impulse is 2 pi, for example, right? So this is 2 pi delta omega. So now question is, if I ask you, what are the frequencies present in this signal? Okay, this is a constant signal throughout, so it's a DC signal per se, right? What is the frequency does it have? It has one single particular frequency. What frequency? It has zero frequency, right? Because it's a DC signal, and that is what the Fourier transform tells me. So this is what the Fourier transform tells me. The Fourier transform tells me that this DC signal is a zero frequency signal, and what is the particular amplitude of the zero frequency signal? That's 2 pi, right? The amplitude of the particular zero frequency signal is 2 pi, right? So with that said, that's the assumption, that's the total discussion here today. We are going to end the discussion today because we had plenty of other what should I say, agenda here, but we shall continue that on the next class. But I believe you understood the idea, right, behind this. By doing Fourier transform, you can see the internal composition of the signal, and again, from the perspective of the system, exciting a system with an impulse is like exciting the system with every possible frequency. Okay, and that is why the impulse response of our linear time invariant system encapsulates the entire behavior of the system. So we discussed quite a few important interesting things here. So with that said, we are going to end today's discussion at this point. I'm not going to prolong this class any longer because if I keep on prolonging this class, you would be hard pressed to understand anything really. So that will be our discussion, end of discussion today. But I would leave a homework for you, a homework designed in a way that you can actually work out from this, from the things that we discussed earlier, right? So my question, or rather a homework question, again I would ask you to do that by yourself, but if you cannot, I will of course help you, don't worry. Okay, my homework would be, homework for you would be to actually calculate the Fourier transform for signum t. What is signum? So this is your homework, and again we're going to do that. If you are unable to do that, we're going to do that on the next class anyway. So this is your homework or assignment, whatever you want to call it. Okay, so calculate. Like if you have any query, please feel free to ask here. Okay, and what is signum t? Let me just tell you that signum t gives you the sign, SIGN, sign of a signal. Okay, this is how it is defined. This is a value of -1 when t is negative. This has a value of 0 when t is equal to 0, and this has a value of +1 when t is greater than 0. That is how the signum signal is defined. So I'm asking you to find out the Fourier transform for that, which you should be able to do using whatever we have studied today. You should not need anything beyond that. With that said, if you are unable to do this, of course we are going to actually do that in any case on the next class, but I would request you to actually try this at home, because as teachers we know that unless you actually try solving problems by yourself at home, you won't learn anything. You might think you have learned, but you won't. Okay, so this is the signal we are talking about, this signal. And again, please submit the assignments that I actually gave you earlier, because as you might already have guessed, this lockdown might be prolonged even further. You might not have the opportunity for a final exam. There could be plenty of other things. So under those scenarios, your evaluation would probably be done based on how you did during the classes, right? So please try to submit the assignments. Again, if you submit a wrong answer, I would help you to realize the correct answer. And this is the point, and this is the kind of the midpoint here. Okay, and there is of course a jump discontinuity. So that's the signal we have. That's the signal. Right. Oh, and as since we are electrical engineers, let's draw the jumps as well. Right. So that is what the signal looks like. So your job would be to actually, or homework assignment would be finding the Fourier transform of this. Again, you won't need anything that we haven't discussed today, right? In order to calculate this. Try this at home. And yes, with that said, please let me know if you have any query. I'll be here for 5 more minutes and we shall end our discussion today. We had a good class. We did not have any technical issues from my end at least. I believe I got the ideas through to you, right? Again, I shall give you the handouts and the Python program we discussed. So no worries on that. And again, if you have any query regarding anything after the end of the class, feel free to drop me an email. Okay. So my email ID would be, of course, I believe you know already. I have been sending you plenty of emails. Okay. Right. So with that said, and again for attendance, if any one of you have attended the class plus but did not write anything on the live chat, please write something on the live chat so that I actually get to know your name, so that I can give you the attendance. That is how really attendance works here. If you don't write anything, I won't be able to. I will be hard pressed to know who you are, right? So all right, thank you to all of you for joining the classes, and stay safe. I'll let you know about the next class, which is probably going to be on next Monday. Okay, so we shall continue today's agenda, because in today's agenda we had plenty of other problems that we thought of discussing, but we kind of left here, and we shall continue from that on the next class. Probably that's going to happen on next Monday. So with that said, we are going to end the stream today. So thank you for joining. I will see you on Monday.